Hello, just one second while I get things set up here. Okay, so hello, I'm Brian Gill from Pittsburgh Supercomputing Center, and I'm going to talk a little bit about Hadoop and Spark at PSC today, and specifically just an overview of both what they are and what they do, and then also how we've attempted to make what seems like a system that wouldn't necessarily fit well into a scheduled shared HPC environment, how we've made that work with our setup, and possibly how others can as well. So without further ado, let's jump in here. So what is Hadoop? Hadoop is a programming platform for processing big data. It includes a file system, a software ecosystem, which has become more important as the years have gone on, and the actual Hadoop interfaces themselves have kind of dwindled in performance. And finally, it's a stuffed elephant. The system is named after Doug Cutting's child's stuffed elephant, and it's pretty cute. It was created as an open source implementation of the MapReduce system that was presented in a paper in, I think it was 2004 by Google at OSI, and then picked up by Apache, and originally by Yahoo and then Apache, and ever since it's been a big player in big data. So what does Hadoop do? It will distribute your files into a file system, which provides replication and also allows you to do computation closer to the CPU, which has certain advantages, which we'll talk about. And also it's a computation system. And again, there's a software ecosystem that lives on top of the file system that may or may not use this system. But the basic system that is provided for you is the MapReduce system, which again, we'll talk about in just a little detail here. So MapReduce is the new idea. It maps key value pairs to intermediate key value pairs and then reduces them into some kind of a human readable or at least human usable result. There's a map function in every program and then a reduce function. The map will apply a function basically to everything. Sometimes the reduce will actually just take that output, and sometimes it will do some kind of filtering on the results and aggregate them into a sum or some other useful number. So let's talk about some of the components of Hadoop. There's the HDFS, which is the Hadoop Distributed File System. This is not a file system that you install on your computer, not something you install directly. Instead, it's a meta file system that lives on top of other file systems. It provides replications, which allows A, you can have a failure, you don't lose your data, and B, it also pre-distributes the data so that you can move the computation easily to where the data already is, which saves you a lot of time. I like to tell the story about how when I started at PSC, one of my first jobs was setting up caching to move data into and out of the supercomputer, which was Lemieux at the time, and then shortly after Big Ben. And the reason for that was that there was a limited amount of space that could be accessed easily by the machine, so we had to get stuff in and out of it as quickly as possible. The idea here is not to ever have to do that, and to the greatest extent possible, not to have to move any data around at all. This does raise a conflict with the way that shared HPC systems typically work, which we'll get to in a minute. The HDFS also is designed as the write once, read many, or worm file system, which gives it some advantages for streaming throughput. It's not a typical it's not your typical file system that will allow random access. You can contrast this with an RDBMS or even normal file access within POSIX. But you can do things like, with certain limitations mounted on fuse, etc., and treat it like a normal file system for most respects. But the point being, though, that the kind of work that you're doing on here is meant to be shuffling through the whole thing as quickly as possible and not looking for individual lines in database records or things like that. Okay, once again, it's a meta file system which requires an underlying file system, and it has special access commands where you can do exports using fuse vendor file systems, etc. And just a quick overview of what the HDFS architecture looks like. We have a name node, which is the daemon that holds the metadata for the system. And then the data is spread out in blocks onto the data nodes. The system is both node and rack aware, so that it can spread your data out in the most failure resistant possible way. And it's also configurable so that you can have as much or as little replication as you like, spread out among all the nodes in your system. You can also have replication of the name node. The daemons are the name node, which serves the metadata, and then the data nodes, which live on each of the worker nodes, which holds the blocks, and then also you typically serve also as a compute node again, to keep those things close to each other. Okay, so I don't want to spend a lot of time on this, but I just wanted to very quickly touch on how Hadoop works. Yarn is the yet another resource negotiator, which replaces the original MapReduce system, which was the programming interface for Hadoop. But it's also included as an API, which is compatible with the older 1.x versions. And it's designed to assign resources for applications and be basically a more generic interface for programming on top of the Hadoop system and your Hadoop data. The data is really the key here, and that's, I think, why there's so many different pieces of software that use the file system and then completely ignore or barely use Yarn for their work. There's things like HBase, things like Pig, and Spark being a notable consumer of them, which we'll talk about in a little bit of detail in a moment. As time has gone on, the Yarn system and the MapReduce system have kind of dwindled in importance, and these other pieces of software have overtaken them. But they're still there, and they're still used for some things, either as components or even just outright to do your work in a MapReduce system, if that's the way that you like to do it. The Yarn system, again, has sort of a controller daemon called the resource manager, which includes an applications manager and a pluggable scheduler. And then the node managers, which are the worker nodes that live on each of the nodes and hold the containers, which are tasks from the application managers. And then they can be elected as the application to run each of the applications, which we'll see in this diagram here. So the application master will be on one of the node managers, and then the resource manager will be the one that assigns them. And you can have more than one working on any particular one. And again, it's the metadata server, the node name, the node master, node manager rather, is, the name node is aware of where all the pieces of data are. So it will assign the worker nodes based on where the data they want to work on is. And to the extent that that's possible, it'll just do that outright. And if it's not possible, then it'll do the minimum amount of shuffling required in order to get the blocks where they need to be worked on. Okay, so let's talk a little bit about how we've made this work and what some of the challenges are within our existing shared HPC environment here at PSC. So one of the assumptions that we have is that a typical Hadoop user is going to have a ton of data. The whole point of using Hadoop for the most part is that you find that typical methods of handling your data, like using an Oracle database or something like that, start to either become prohibitively slow or prohibitively expensive for handling the extremely large amount of data that you're accruing. For instance, if you're a large corporation and you've got a lot of logs, or if there's all sorts of situations where you could end up with a whole lot, a very large trove of data that you don't want to move around and that is too big to easily fit into sort of a sharded RDBMS approach. So typical users will have a ton of data. However, the traditional methods of looking at things aren't going to be easily available to help you, so you want to use this very large system of data. However, trying to make all of this work on an HPC system isn't necessarily easy. Typically, they'll have a very large data set, which is chewed on in parallel by commodity machines. It provides redundancy and error handling and brings the computation where the data is. However, in a typical shared HPC environment, the daemons only run as long as your job does, so they won't be consistently available. The file system doesn't persist between your jobs. Perhaps you have a file system on the back end that is persistent that you can store things to, but also the shared file systems really negate the locality advantage, meaning that the idea of bringing your computation to where the data is so that you don't have to move it around. If you're loading stuff into and out of your job into the file space, then you're not really getting that advantage because you're having to move it in the first place anyway. Or if it's already there, but it's on a shared file system that doesn't perform well in parallel necessarily, or as well as local anyway, then you're really losing some of that advantage. So we found some ways to compromise and make things work in our environment. So basically, you'd wonder who would want to come and try to work on a system like this, when typically you're going to have terabytes or petabytes of data that you're going to just want to let sit there and sort of chew on them forever. Whereas almost everyone in the PSC and in Exceed is going to have a relatively limited number of service units available, and they can't just reserve the whole machine forever. However, we do have a few specific kinds of users that that find that it's very good, that this environment can be very fruitful for the work that they're doing. Some of the biggest ones are educational users. There's two different main categories of those. The workshop participants for our big data conferences. We've had up to 600 simultaneous users all running Spark jobs on bridges. And that's been a pretty big achievement. We have a pretty minimal environment for that, but it started out with the larger cluster-based version that we initially set up. Another common case is educational users. These will typically be people teaching a class and needing to provide an environment that is in most respects the same as a real Hadoop environment, although possibly at a somewhat smaller scale. And finally, we have your dabblers, I like to call them, but anyone who's experimenting with learning on prototyping, testing, just using a small Hadoop environment where they want to have access to a cluster, but they don't necessarily need a sort of full-scale and permanent solution. So we have set up a 3-tier system that has worked well for most of the use cases that we encounter. The first one is we have standalone Spark for workshops. So we've iterated over this over time. We initially started out with a Hadoop and HDFS backing for all of the users at our workshops. We found that worked, but it didn't necessarily scale performance-wise as well as we wanted to for the kinds of work that people were doing in those workshops. So instead, we made some changes to the environment to allow Spark to work standalone with the background, with the normal shared file system, our Pylon system, but also expanding the amount of ports, the number of ports that are available for the Spark system, and also massively increasing the amount of connections that are available to the metadata backing store, which happens to be a MySQL database in our case. So these things, if you tried to run just 2 standalone Spark instances on a single machine, you'd quickly find that they all tried to vie for the same resources and have a lot of errors, but we've managed to scale this up pretty substantially, and really we don't see a limit to how many people we could accommodate, and we've been basically breaking records every time we run the big data workshop, so we'll see how high that number gets. The second solution that we found is the ad hoc cluster approach, and this is the one that's documented on the Bridges user guide. The notion here is that you'll start with a few nodes and create your own standard Hadoop environment, just vanilla Apache installation by default, and basically run a script and have a working Hadoop environment. Everything goes away when you're done, but you can certainly pull the files out of it if you need to when you're done. And we also have persistence options available for those who want to periodically reuse such a cluster. But for most of our more permanent users, we also have a fixed infrastructure cluster, which I'll go into detail about in a minute. So once again, the standalone Spark, we configured things to use a central metadata backing store and configured it for currently upwards of 10,000 concurrent connections to that backing store database. And relax the range requirements for the nodes for the Spark, for the same node sessions rather. So we end up having on 28 core nodes, we end up having 7 concurrent sessions, and that's turned out to be good for the. I don't want to say that they're toy problems because they're definitely real work. And in fact, if any of you have attended John Urbanek's talk on Spark over at the Big Data Conference, we go through the $1 million Netflix prize, which was a pretty significant and real computation problem just a few years ago, which can easily be done in that level of resources. But of course, if you want to do work that's not educational and scale higher, that's certainly possible and available, but not in this simple arrangement. Okay, the ad hoc Hadoop clusters, again, anyone can walk up and use them as long as you have an allocation on Bridges. You start with a job with 3 or more nodes and just run a setup script and you have it. It's a minimal real Hadoop setup. It's good for testing or learning. It does use your SUs relatively quickly because you have to have a minimum of 3 nodes and you have to use all the cores on them. So compared to, say, running in a shared instance, you are using some degree of resources, but it does help you to have basically a pre-configured cluster setup without having to go and do all of the setup yourself or work with the limitations of some of the vendors that, that provide these things. It's a little more configurable, perhaps. Finally, the infrastructure cluster. So earlier this year, we set up, after doing a lot of work on different ways that we could accommodate our users, we found a pretty happy compromise here. And that is to have 6 dedicated nodes for a semi-permanent cluster, at least, indefinitely going forward. It's expandable on demand, but 6 nodes with 28 cores each has been enough to handle most of the tasks that our users have wanted to throw at it so far. Shared access, meaning that more than basically everyone who is allowed to use the machine could be using it at any given moment, and no one has a monopoly on it. As a result, and it also provides a persistent FS, but since it's a shared model, we also have a partial charging model. So currently we charge something like 1/3 of the cost. This also helps to reduce the strain on everyone's SU budgets, because since it's going to be a permanently available cluster, it's using up these nodes 24/7, which means that they have to be charged for all that time. And if you haven't tried to look at how long, how expensive it would be to run 6 nodes for 24/7, it takes quite a lot. So that's spread over several different projects, and it's been modestly successful so far. And if you or someone you know has an interest in having access to a cluster like this, we'd be happy to hook you up with access to it. Okay. Let's see, did I cover all of this already? It's semi-permanent, works like a real fixed Hadoop cluster, persistent file system. One of the advantages of having this also is that it conveniently provides access to the web interfaces. So our network interfaces on bridges are not usually available for typical jobs for security reasons, but for the fixed cluster, which is on predictable nodes, we've set up access under certain circumstances to the web interfaces, which are very useful when you're actually trying to do work with Hadoop and Spark and the other systems. And finally, we make it possible using software modules to configure the software environment per user. So the same version of the Hadoop daemons will be running all of these, but you can use different versions of Spark, for instance, or different versions of HBase or Pig, or whatever it is that you want to use on top of these, and they can all use the same Hadoop system at the same time. The watchword in all of this setup has been flexibility. The 3-tier setup covers most of these cases. We have had some cases where people want to do some experiments running on larger clusters, possibly non-shared ones, to try to get a little bit better performance or better scalability, and we're able to accommodate those as well. This whole setup is easily adapted and scaled depending on your needs, but usually those 3 cases are pretty good at covering most of the cases that we've encountered. And so we find ourselves in a position where we're not able to accommodate everyone who would like to just bring all of their data and just dump it and let it sit there forever. But people with a certain kind of a certain amount of data and amount of work that they want to do on it fit pretty well into our environment. And the educational the different kinds of educational work that are done on Hadoop and Spark have been, this is almost an ideal arrangement for them to try different things out and see how they work. So that's all I had for today. I'm more than happy to take any questions that you have.
Great. Thank you very much, Brian. So do we have any questions? All right. Well, everybody is thinking. I just have a few quick questions.
Okay.
So this infrastructure cluster, and I saw you had it in quotes, the 6 dedicated nodes. So those are nodes that have been carved out of bridges?
Effectively, yeah. They're an indefinite reservation
right.
That's being held for all the projects that are paying for a share of it at any given moment.
Okay. And
so, yeah.
And what are some of the use cases for that on that infrastructure cluster? So you mentioned earlier, like using standalone Spark for workshops and so on, and there were also the ad hoc clusters. But what is being run on the
users?
What one that I remember, this is Phil, Bob, just that. So some people wanted to try out these algorithms for some large scale metagenome analysis and clustering of metagenomes by organism and such. So one that touched me, on the science side. So.
Yeah, and incidentally, I get called in relatively often to help out with some of the projects that people want to do here, but a lot of the work is, as far as I'm concerned, anonymous. I mean, people will come up and just run their own cluster and do their work and not consult with us because it is self-serve to a large extent. When they decide to scale up to a certain extent, like if they decide they need more than 8 nodes or something like that, then they typically get in touch with us. But the nature of it is that we don't see everything that's done.
Excellent. Do we have any more questions for Brian? Well, if not, I have one more question. Earlier in your presentation, you mentioned about some of the limitations of running Hadoop and Spark on bridges, and one that you mentioned was that you're using the shared file system. Of course, that negates some of the locality advantages. So, bridges does not have any node local storage, or is it?
I actually forgot to mention. I had it in my notes to mention in one of these slides, and I forgot to mention it. There is some serial attached storage, which we use as effectively local, which is separated from which each node can treat as local, and that has worked well as sort of pseudo local storage for the nodes. We've also done some things in the past, like when we were working on black and white using RAM disk. And other options when the amount of space required wasn't necessarily as high and performance was more important. Typically we use the node local storage arrangement, but we also sometimes use, when we want to do persistent ad hoc clusters, we'll actually just store things to pile on. We don't get the same performance in that case, but it becomes very simple to save and restore a session between runs. So we haven't done that as much because most of the users who have been doing it that way have found that the permanent cluster works better for them. But that is also a way that we can do it. But again, there's a trade-off in performance when you do it that way.
All right. Do we have any more questions?
I do have one question. I'm curious, I don't know Hadoop that well, but you mentioned a couple of the advantages to using Hadoop, like replication and so forth. Are there good use cases where just using Hadoop as sort of like a way to distribute systems is a good usage without all the additional software that you say can go on top of that?
Well, it's hard for me to imagine one these days. And in fact, it's funny, I went to a talk that one of the Yahoo people did in the early days of Hadoop, and they said that their internal cluster, they had to stamp out some people who had figured out a way to run MPI on top of Hadoop. And kind of bypassed the whole MapReduce system when they had work that didn't fit well into the MapReduce framework. So the answer is that there are use cases, typically things like when you're looking for very simple, almost like grep type of situations out of very large files. Those are cases where MapReduce can be very efficient. Or for instance, it was pretty efficient at doing the TerraSort. It won a prize sometime in, it was like 2009 or 2010. It was the fastest terabyte sort ever. However, things like Spark, which do a lot more in-memory kind of work, have really largely superseded it. And the details of how Spark works is a little beyond this, but I encourage you to attend the big data seminars that we do periodically, and you'll get a deep dive into how Spark works and what you can do with it. And so there more or less, I can't think of a situation where Hadoop would be the easiest or best way to do it. But I also, having seen both, that's how I feel about it.
Okay, thank you.
Sure.
And can I just add, Brian, just a quick clarification there? I think, so I think because when you talked about spinning up a Hadoop cluster, but then people can run Spark and such, I think in that case, is it that Spark is using the Hadoop file system, the HDFS, for some of its data needs, but a lot of people, maybe more people now are running Spark on top of that because it's faster.
Right. Well, in fact, that's how Spark started out. Although you don't have to, you can run Spark on any file system, but
right.
But it's aware of and takes advantage of the advantages that HDFS provides. The way that we run it by default, if you run Spark on top of Hadoop here at PSC, we have it configured where Spark will actually use Yarn, which is again the sort of the programming interface for Hadoop now, as an intermediary to distribute the Spark workers out among the nodes, and again to use that HDFS. It's possible to configure it more than one way, but that's how we do it.
Thank you.
All right, and we have one more question that just came in through the chat. Benjamin Tovar.
I'm looking at it. So wondering if you could talk more about the ad hoc clusters. Do you have several batch jobs running Spark workers? And does the Spark master also sit on a batch job? I may have just inadvertently answered that. So the cluster will have the Hadoop daemons running on each of the nodes in your cluster, and it's configurable the way we have it set up between 3 and 8 nodes, or if you want larger ones, then you have to make a reservation. But when you set that up, the Yarn daemons run, and when you run Spark, it talks to Yarn, and that actually starts all of the Spark workers on the different nodes. And it reads out of and writes into the HDFS, and you can pull that replicated data out when you're done.
All right, thank you so much, Brian, for the great presentation and for fielding all those questions at the end.
Yeah,
so let me ask you to unshare so that we can switch over to Laura Carrington.
Hello?
Yep, we can hear you. Go ahead whenever you're ready.
Sure. So I'm Laura Carrington, and I'm actually going to talk about my ECSS project and developing a coupling interface between what was a Kinetic PUI code written in Fortran and an MHD code that was written in C++. And this work was done on the Stampede2 system at TACC, and I'm going to present sort of the method I used, a couple of the codes, as well as some lessons learned. Okay, so first, let me just describe the objective of the team. And it was really to sort of gain an understanding of the dynamical heliosphere, both from the solar origins to its interaction with the local interstellar medium. And they wanted to do this by creating a suite of data-driven models from the Sun to the LISM connection. So the initial use case that they wanted to apply this to was in examining Voyager 1 data. So they wanted to use the simulations to model the GCR trajectories at some point along the Voyager's path. And the idea being that they would be able to show a strong correlation between the GCR variations and the structure of the solar wind LISM transition region. So that was their main initial use case that they had. So the first step really here was to take the original initial serial code and parallelize it. So the PUI code actually models these non-thermal ions that are created when a new population of neutral atoms are born, both in the solar wind and in the LISM. Now these ions then generate turbulence that heats up the thermal ions, and the PUIs are then accelerated to create cosmic rays. So the PUI code essentially models the trajectories of these cosmic rays. It was originally a mix of Fortran77 and Fortran90. So it had both modules and common blocks. It was only designed to compute a single trajectory of a single particle. So the second code was a global magnetohydrodynamic code, or MHD code, that simulates magnetic fields. And it uses then an AMR method where it distributes the work to computational nodes via what they call patches. And since there are different levels of refinement, the amount and the resolution of the data in these patches varies. The code was written in C++ as well as Tarn++, and it is a parallel code. So the idea was to use the magnetic field data from the MHD simulation in the PUI trajectory calculations. So the first step in the project was to parallelize the PUI code. And to do this, I created a pool of trajectories that were to be computed. And this involved new data structures to hold the values and changes to the way the random seed is calculated for a given trajectory. At each step in the trajectory, magnetic field data is needed from the MHD code. So these trajectories take a single step and then get data from the MHD code. The data is based on the coordinates of that trajectory. So initially, since all the trajectories start at the same point and radiate outwards, the data for that single point and initial steps is from the same patch. So the reason a pool of trajectories was created because each trajectory could take a different number of steps before it reaches conditions for completion. So that means some trajectories could take 200,000 steps while others will only take a few thousand steps. By having a pool of trajectories, each MPI task keeps computing a new trajectory until all the MPI tasks have finished their first trajectory, or some limit of trajectories have been computed. So the idea that everyone had to compute their first trajectory is that certain trajectories would take, say, 200,000 steps before they're terminated based on certain conditions. We didn't want those what I call long-running, long-stepping trajectories to be cut off just because everyone else had short-running trajectories. So, because statistically all the trajectories are combined to create a flux. So for some runs, we actually had well over 5,000 trajectories computed because some of the MPI ranks took these excessive amount of steps before terminating their trajectory calculation, which enabled the other MPI tasks to compute many trajectories. So also part of the parallelization was the management of the output for each trajectory. Again, since some of these MPI ranks would compute multiple trajectories, they needed to be tagged in the output as a start of a new trajectory. Also part of this was debugging the actual calculation that used that magnetic field data. So certain trajectories became problematic, and debugging those problems required some additional output features. And finally, in parallelizing the code, I tried to keep the main structure of the trajectory calculation code similar to the original, so that the developer of that code would understand it and be able to modify the original calculation. Basically, they could go back in and make modifications to the original calculation and not really have to worry about any any changes due to NPI or parallelization. So in order to do this, most of the parallelization setup and the management of the trajectories was implemented in the main structure of the MHD code. So one of the challenges of the project was due to different parallelization or data layout strategies. And this slide, I try to show a sample first of how the MHD data is laid out. So moving from left to right, the first image is the MHD data along the path of Voyager 1. And in the next image, the data is decomposed into 16 patches. And this is a very simple decomposition, not meant to represent what really the details of those 16 patches. The final image is just showing how these 16 patches might be distributed to the 16 MPI ranks. And note that this is very simplified view of this distribution. So next, try and show how the trajectory computation is distributed to the different MPI ranks. So in the calculation, we take a single starting point and compute around 5,000 of these trajectories. So we have a pool of trajectories to compute, and initially each MPI rank is given one trajectory to compute. And when it finishes that, it will go back to the pool and grab another to compute. So note in this example, I'm just saving space and only showing 8 of the 16 ranks that were distributed. For this code, the general runs that we did were on around 2,000 MPI ranks. Okay, so the main reason to couple these codes is that in computing the steps in the trajectories, the PUI code uses magnetic field data from the MHD code. So we call this process extraction of the data, which is done by each MPI rank searching its patch of data to determine if that point in the trajectory is within its patch. So this search is done in parallel by giving a list of points to every MHD rank. The points are the locations of each trajectory currently being computed. So for any point where there is a match, then the data is returned to that specific trajectory's MPI rank for its next calculation. So this transfer of data back and forth, the points of coordinates and the magnetic field data, is done through a series of global tables. So here I'm just showing an example of creating this global table for a coordinate, for the coordinates of each trajectory. So we want to have a single table that the MHD code can use to search its patches. So this is showing an example of how this global table is created and communicated to the other MPI ranks. Essentially, each MPI rank starts with a table filled with zeros. It places the value of its X coordinate in the row of that table that corresponds to its MPI rank. So it knows in these global tables to always look in the rank, in the row that matches its MPI rank ID. MPI all reduce is then used to sum these tables from each MPI rank, creating a global table with each MPI rank's coordinates. So this process is done for the X, the Y, and the Z coordinates to create these 3 tables. So here I'm just showing an example of the global MHD parameter table alongside the coordinate table to see how the 2 codes connect. So similar to the coordinate table, the MHD code creates a parameter table that is propagated with the parameters for that corresponding coordinate. So again, similar to that coordinate table, the MHD code has each MPI rank create parameter tables with zeros. Then it searches its path for the coordinates for all those coordinates. And if there's a match, it fills in that particular row with the parameters for the match. So some MPI ranks might fill in multiple rows and others might fill in none, depending on where the trajectories are and what their patch data includes. So then we use MPI all reduce to sum the tables and create a global table with all the values. Now, each MPI rank for the PUI table can get the parameters for its coordinates by basically looking in the row that corresponds to its MPI rank ID. So, not sure if this is new information to people, but some of the, I just wanted to go over some of the lessons learned along the way in combining the two codes. The first was really in defining names of Fortran routines in C++. So depending on the system you have, routine names can get mangled a bit, or underscores added or not, and it also depends on the compiler. So to help in compiling and linking this code on multiple systems, because they run these codes both on Stampede as well as systems at NASA, I use a keyword bind to force the naming of the Fortran routines. So in addition to binding of the name in the Fortran code, you also needed to define the routine as an external function in the C++ code. So also, a lot of the existing Fortran code used common blocks. And I sort of wanted to keep the structure looking the same for the developer. I had to use the common blocks to transfer some of the data between the two codes, as well as within the Fortran codes. So similar to using Fortran routines, I needed to use that bind keyword again to basically bind the name of the common block in the Fortran code. And in C++, then I needed to define an external, define the common block as an external structure. And by doing that, basically I could modify any of those existing values in the C++ code, and they would easily be exist in the Fortran code when it grabbed those values. And then I guess for a lot of my ECSS projects on the TACC system, I learned some interesting facts about compiling for vectorization. So both the Skylake and the KNL have the capability of 512-bit vector instructions. Now, if an application can vectorize well and take advantage of these longer instructions, then it will improve the performance immensely. And this 512-bit vector instructions was a main selling point of the KNLs. And also the standard, what I call the standard AVX 512 flag on the KNL provides these 512-bit vector instructions if it's possible. But what I found out for the Skylake is there's a bit of a catch when using these instructions. So on the newer processors, I believe starting at Haswell and Broadwell systems, these vector instructions will normally heat up a processor. So to counteract this extra heat, the processor will sort of start to look ahead at upcoming instructions. If it sees vector instructions, it will slow down the processor in order to keep it cool and not overheat. The problem with the Skylake is that for 512-bit instructions, because this is the first Intel Xeon mainline processor that included these 512-bit instructions, the processor actually really heats up. So the processor, in order to counteract this, they really downclock the processor or slow it down immensely. this slowdown can really hurt performance if the code does not perform a lot of 512-bit instructions. So if it's only using the 512-bit instructions sparsely, the clock will still get turned down and slow down the processor. So understanding this big performance impact of these poorly vectorized codes, that default AVX 512 flag, which in your mind, if you're compiling, would provide 512-bit instructions, actually only provides 256-bit instructions. And that's because the down clock for 256 instructions is a lot less than for 512. So in order to get the full 512-bit instructions, you need to add the additional QOut flag in your compiling. In addition, what I found for some of the codes that I looked at, the older AVX2 flag was often faster than the default AVX 512 flag, even though I believe they both provide 256-bit instructions, but there may be additional optimizations or downclocking due to the 512, the AVX 512 flag. And that is the presentation. Any questions?
Hi, Laura. I was wondering if the code that you made to bridge these two is available online somewhere.
So the code that I used to bridge it, I embedded into the existing MHD code. So basically taking the Fortran code and breaking it up into routines that then I could call from the MHD code, as well as the main loop structure of stepping each of these trajectories. I created basically within the MHD code and the pooling of the trajectories. So the MHD code itself, I believe, is open source. It's called MS Flukes. And if you wanted to look at it, you could send me an email and I can check with the PIs and see if they're okay with that. But I'm pretty sure it's an open source code.
Okay, thank you. And one other question, I was wondering if you know about sort of the science results of running this, these calculations, if they discover something scientifically interesting.
So the use case that they're working on now, I think that is scientifically interesting, and it's that showing that correlation between those cosmic ray variations and this transition region between the solar wind and the local interstellar medium.
Okay, thank you. Very nice presentation.
Thanks.
Do we have any more questions?
This is Phil. And I apologize if I missed this, because I had to step away for a second. How did you verify if the codes were actually using the 512 vector instructions?
I have a tool that instruments the binary, and helps me determine the vector length that I was using, and basically it's looking to optimize the code. And when I realized I was compiling with 512 and wasn't seeing any 512 instructions, I started to do some tests on codes that like stream where I knew it should vectorize well. And then I had a separate project with Intel, and I asked them, some of their experts, why I wasn't seeing 512-bit instructions, and that's when they explained these flags.
All those details. That's really interesting. What tool were you using? Can I ask?
It's called Pebble. It's a binary instrumenter. It's similar to PIN. So it gives me an instruction mix.
Okay, so it wasn't like Intel's tools or anything but I haven't heard of Pebble, so that's
Yeah.
Phil, let me just cut in real quick.
Sure.
Laura, if you could paste the link for Pebble into the chat, that would be great. Because I remember Pebble has like most of these things in unusual spelling.
Yeah, let me see if I can get the GitHub link.
yeah, that'd be great.
Can I stop sharing for a moment?
Oh yeah, go ahead.
I've used a variety of these tools in the past, and so I'm always interested in what people are doing.
Yeah. So one interesting thing about